planetary disks. So let's see. Matthew, great. Yeah, take it away, Matthew.
Can you hear me? Okay, good. Okay, yeah, so thank you. My name is, again, Matthew Yu. I'm a fifth-year graduate student from UCLA. Today I will be sharing my current work on modeling super-Earth's migration in magnetospherically truncated planetary disk. And this is a work in collaboration with Yoshihiro Hasegawa from JPL and under the advice of my advisor, Brett Hansen from UCLA. So in this talk, oops, one second, it's fruit first. Okay. Yeah, in this talk, first I would like to introduce you to a little bit on the exoplanet occurrence side of things, and then I will go over what is the current state-of-the-art sort of modeling on like how people are treating the inner region of the protoplanetary disk, and then after that, I will go into what kind of model we are trying to present and what kind of prediction we can get out of this type of model. So first off, exoplanet occurrence. So on this plot, on the y-axis, we have the planet radius, and on the x-axis, we have the period where the planet are orbiting around. And on this plot, most of the dots are green, which indicates that most of these planets are observed by the transit method. And because Kepler have done most of the work, so most of these planets are actually around Sun-like star. So for the discussion of the rest of the talk, we will be considering planet around Sun-like star. So whenever you see on the orbital axis, on the x-axis, those are calculated based on solar mass whole star. Okay, so in this particular population, we can further subdivide it into a group that we call the super-Earths and the sub-Neptunes. And if we look at specifically occurrence of these particular type of planets, this is a plot that I stole from Eric Protoplanetary, which he did a work on looking at the occurrence of this type of planets. And if we look at this particular plot, we see that fairly weirdly, there is a peak in occurrence of both super-Earths and sub-Neptunes on around 10 days orbit. And however, if we look back into our own solar system, on the 10 days orbit in our own solar system, there's literally nothing. The closest is 88 days of Mercury. So the exoplanet system seems to be fairly different from our own solar system, and because of that, probably worth like actually figuring out exactly how those planets ended up there. And regarding this topic, people have proposed certain explanation for it, and one of them is that okay, if we want to put planet in 10 days, might as well, like let's say that the protoplanetary disk is truncated at 10 days because the stellar magnetic field overcome the accretion flow at that particular location. And so now that this is cut off at 10 days. And in this particular picture, the planet would be forming exterior to this 10-day orbit. And while the planet is formed exterior, the planet would interact with the disk material itself. And in the case for super-Earth and sub-Neptunes, most of the time, the planet does not open up a gap in the disk itself, which means that through the interaction, the planet itself would experience type 1 migration. And even though type 1 migration generally depends on the local disk property, but for most disks, we will see that the planet would go slowly towards the whole star itself. And if we put that back into the picture of how people have been trying to explain how the planet ended up there, this type 1 migration would slowly put the planet closer and closer to the 10 days truncation. And once the planet reached 10 days, the planet is basically assumed to be trapped at that particular location. So then voila, you have planet at 10 days orbit, and problem solved, right? So this is the most simple picture that you can imagine for this particular case. But in other field, such as in the neutron star accretion in this case, there were already works that have done slightly bit better modeling on this type of like trying to assume magnetospherically truncated inner edge of the disk. And the main thing about this model is that it also consider not only a sharp truncation at the disk, the sharp truncation at the inner disk, but it also add in the influence of the magnetic field itself on the inner region of the disk, not only the teeny tiny bit of the truncation. And so we would like to apply this particular model on the protoplanetary disk case, which goes into our own disk model, which we still consider that there would be a magnetic field truncating the disk at roughly the same location as the previous model have shown. But we also consider that the magnetic field is now threading through the disk and interacting with the disk material. And the last 2 points is that we would like to also consider that there are two types of main heating source in the protoplanetary disk itself, which first one is that the disk can be heated up by the whole star irradiating on it, and then we would also like to consider that the accretion itself would heat up the disk and providing heating source to the disk itself. And if we put all of those together, we arrive at this particular disk model. So we still see that there is a inner cavity or inner truncation at the very inner bit of the disk. But now we have an extra region that is exterior to it that we call the transition region. And if we look at this particular transition region, its main characteristic is that it is strongly influenced by the stellar magnetic field itself. The width of this particular region is mainly controlled by the balance between the magnetic field and also the accretion flow that is going through the disk. And the most important thing is that the angular momentum of this material in this particular part of the disk is being extracted by the magnetic field from the star, and this can be modeled by just considering there being a little bit more viscosity in the disk, and hence changing the surface density and temperature structure of the disk itself. So if we consider this type of disk and put in some fairly generic disk model parameters and using migration prescription from Peter Cooper et al. 2010, and assuming that the planet inside of this have roughly 0 eccentricity, we can arrive at a migration map that looks like this. And on the y-axis, we see the mass of the planet. On the x-axis, we see the orbital period of the planet. And the transition region is labeled on the graph. The main takeaway of this graph is that the red color means that the planet would like to migrate outwards, and the blue means that the planet would like to migrate inwards. And in this particular case, you will see that if the planet forms exterior to the transition zone or transition region, it will slowly migrate in and basically get trapped in between the red and blue region. So for this particular generic disk, we see that the planet would like to pile up at 19 days, which is sort of like a factor of 2 compared to the case that we saw earlier that is seen in the observation. So probably we need to try to consider a weaker magnetic field to reproduce the observation, which here is some preliminary results of what consider a weaker magnetic field would do to the transition region and where the planet would be trapped. So if I cut down the magnetic field by a factor of 10, we arrive at roughly a slightly bit more than 2 days. So So probably in the reality is somewhere in between 100 gauss and 1,000 gauss. So apart from this, we also have to consider that the disk itself is also dissipating. And this brings us to the full modeling that we will have to do the next step, which is including a actually dissipating disk itself, which would result in the transition zone moving outward slowly and as the disk dissipate. Okay, so I would, yep, and also we would like to verify the results by using simulation, and hopefully this will be done during the fall, during this fall, and we will have more results down the road. Okay, here I would pull up my summary, and I see I am almost out of time, so I probably should open up the floor to questions, and thank you.
All right, thank you very much. Let's see if I can get this. I hope that's at the right volume now.
That works.
All right, cool. Yeah, so feel free to put questions in the chat, everyone. We've got one from Isabel Angelo. So interesting talk. You mentioned that you performed the analysis assuming sun-like host stars. Since the IMF peaks at lower mass stars, I'm wondering if and how your results would change for lower host star masses.
That is something that we haven't looked at yet, but that definitely is a direction that we consider. Probably like after we are done with like the analysis of like the sunlight star, we will have to move to lower mass star to look at exactly what happened. But I don't know exactly how it would change it because this is during the early phase of the star's age. So the magnetic field is also considerably different between the two types. So it might be not so trivial as to like just scaling. So I can't really say much about exactly how that would perform.
Great. So I think I have a question of my own. So I think you showed how that transition region is really sensitive to the magnetic field that you assume and also to the time evolution. But I'm wondering if there are independent measurements of that stellar magnetic field that could be made that might help constrain your model.
Yes. So the value that I picked for those particular case is basically taken from T Tauri star measurements, which have a fairly wide range. As far as I can remember, it's like somewhere along the line of like on the order of like 100 gauss to like 1,000 gauss ish. So that's the reason why I showed those two particular value. But yeah, the constraint is there, but it's not like precise as to what's the exact value is.
I see. All right, thanks. And let's wait another few seconds. Yeah, I think we got another question in the chat. Thanks for this talk. I have a quick question about the disk very close in. What kinds of gas densities are expected? Is the gas thought to be optically thick in the transition region?
So actually the gas is, yeah, that's actually like one of the details that we were struggling to reproduce. The gas itself should be, especially like when this is like later time, not like extremely early. That part of this is optically thin usually. Typically not optically thick. Yeah. When we are talking about like 10 to the negative 8 solar mass per year of accretion rates, that part of the disk is generally optically thin.
All right, great. Well, if there are no further questions, let's all thank Matthew again for a great talk.
Thank you.
And